have just one slide. And there's a link to my previous presentation in that some of those data that we analyzed, we started to think about not only how to retrospectively understand what was happening, but rather how to use that information to make predictions. How could we understand certain trends and relationships between large amounts of heterogeneous data and use those trends to effectively create predictions about how some coincident of events at some frequency at some point in time will lead to an event that is not desirable. So in this case, can we understand how a certain coincidence of symptoms at a point in time can lead us to some event that we want to avoid? And so those data that we collected from both structured and unstructured sources, so that would be scientific literature, that would be internal FDA data, it's highly clean and well-structured data, and of course, you heard my talk on social media. So here's what we did. We created even more data from all the data that we collected. It seems kind of counterintuitive to have a great deal of information and then make even more to help understand what was happening. Our first attempt at trying to understand the relationship between certain terms, and just very briefly, how we normalized all that data, which was addressed just a moment ago, we decided to use a standard set of terms called preferred terms that describe specific side effects. It's a taxonomy, mesh taxonomy, medical subject heading index. And if we found those terms in any data source, we would pull those terms out, note the date at which they were identified, and then note what other terms co-occurred, and then note what two dates had terms that co-occurred, and so on and so on and so on. So in essence, the first thing we did is create a correlation matrix, which you can see here at the bottom. And it's nothing more than a relationship between all the terms against all the terms. And the little red dots that you see coming up, those are indicating that there is a coincidence of terms. Now, the human factor isn't necessary because now we have to recognize whether those terms are really significant, whether they mean something important. But having said that, we've been able to identify that coincidence at some frequency across tens and tens of thousands of individual data points. What we did then next is take that correlation matrix and create a correlation on the clusters of those terms. So you can see that what we've done is we've condensed those red dots, and now we've made clusters of terms that you can, well, you can't read them, but you can see they're up there. Clusters of terms by their frequency of co-occurrence. And then we took all that and did a two-way hierarchical clustering approach and discovered a subset at the very bottom then of red. And that red is where most terms co-occurred most often. The problem with this is just a picture of everything that happened in the past aggregated. It offers little to no predictive value. And our approach then was, well, what if we took that and made it a movie? What if we watched that correlation matrix move through time, and as it moved through time, we allowed terms to self-aggregate and associate and cluster, and then we create even more data. Between each two time points, we would extract the absolute change in correlation, or the R-square here, frankly. Then we would extract the rate of change between 2 time points. And then we would take the second derivative of that and extract the momentum. In biology, often momentum, particularly clinically related biology, is incredibly important. One may see nothing, and then when certain events co-occur, then you see an effect. So we wanted to understand basically how that matrix of data could generate an absolute difference, a rate difference, and a momentum difference. So we took a lot of information and made it 3 times as big. And then, so what I'll show you now to finish up here is in each frame is a unit of time going over, I think, 2 years or more. And it's showing you how the red hotspots are clustering terms. And from this movie, we effectively generated 3 more movies. So now you can see everything moving. The blue is inverse correlation, red is correlation. So if I were to stop this movie, and here's where the prediction would occur, I see certain hotspots there. And I look at the terms and I go, wow, clinically those mean a lot. That individual or those terms clinically signify, let's say, a heart attack. What we do then is we play each one of the movies back, watching how any of those hotspots came to be. What terms, at what point, of the vectors, either through absolute, rate, or momentum, that coalesce towards the event, the clinically relevant co-occurrent event. And from that, we could establish that when these terms occur at this point in time, we can actually predict at some point in time, given that constant change, we should expect that event. So we took that historical picture and essentially sort of, not only did we build a lie detector, but we built a time machine. So we went back in time, watched where things started, and calculated how they came to be at a point in time of interest. And so our approach to big data was to make bigger data. And from that, create a temporal network, a map, make it a movie, play the movie backwards, and see where the problem started, and make that predictive. Thank you.
Thank you.